buildings do contribute to sustainability, and building do contribute to energy emissions and resources. 80% of India is yet to be built, and we are going to see a lot of urbanization coming in next couple of years. So if you look at any particular building, there are five major energy consuming sectors in that particular building. So there will be different kind of studies one needs to do in each of these design stage, and then there are different kind of tools which one will require in terms of simulation at each of these design stage. Typical methodology for energy efficient building design. So here there are different kind of studies which are required at different stages. Then Honeybee we can use for outdoor thermal comfort, sensitivity mapping for vegetation, so how shading would impact on a particular design. A very interesting tool and a software which is used for wind analysis. If we look at other set of tools, so we have ISVE, which is industry recognized in terms of energy simulation. How do these tools help? So it's important to understand.
Hello everyone, we are back again. So coming up, we have now a workshop on simulation tools for sustainable design decisions. So let me give you a brief about the workshop. Simulation tools for sustainable design are essential in today's eco-conscious world, enabling architects and designers to make data-driven decisions that minimize environmental impact. These tools allow for real-time analysis of energy consumption, daylight optimization, thermal performance, and material efficiency, helping professionals create buildings that are not only aesthetically pleasing but also resource efficient and environmentally responsive. To shed light on this workshop, we have with us Mansi Parikh. I welcome Mansi to guide us in this workshop on simulation tools for design decisions. Hi, Mansi.
Hi Simran, how are you?
I'm good. How are you?
I'm good, thank you.
It's great to have you here. So let me give a short introduction about Mansi. So Mansi Parikh is a highly experienced sustainability professional with nearly a decade of expertise in sustainable and net zero design practices. He has contributed to numerous projects in India and abroad, aiming for net zero outcomes in energy, water, carbon emissions, and waste management. Her areas of expertise include passive design strategies, low energy cooling systems, energy efficiency, lighting, and daylight design. Mansi has also successfully led projects for green building certifications such as WELL, LEED, GRIHA, IGBC, MOSTADAMA, and BREAM. So, welcome, Mansi. I hand over the stage to you and to all the listeners out there. In case of any questions or queries, you can drop them in the chat box, and we will take it up with Mansi.
Thanks, Simran, for the wonderful introduction. And we'll start with today's webinar.
Yes.
So my screen is visible, right? I think that shouldn't be a
Yes, it's
problem.
visible.
Perfect. All right. So here in this session, we are going to cover a couple of things. One being simulation softwares and how to actually use those simulation softwares through a integrated design approach. So you can have simulation softwares are like tools, but tools would help you define what are the critical aspects in terms of design. It's going to give you some results, but how to interpret those results. So I'm going to take you through that journey and process as well, and through a different design approach. So as an architect, we have a standard design approach, and then there is something called as integrative design approach. So I'm going to take you through that as well in today's session. So let's look at why climate change, why energy efficiency, or why sustainability is important. So as we know that if we move at the current pace, as how we are consuming right now all the resources, we'll require somewhere around 5 earth to manage all of these resources. So we are overutilizing our resources. So sustainability definitely is important, and buildings do contribute to sustainability, and building do contribute to energy emissions and resources. So let's look at it how. So if we look at building industry overall, it uses 50% of water, 50% of energy. They contribute to 23% of annual air pollution, which is huge number, right? And then 60% of resources for building materials like cement, steel, whatever we use in today's daily construction. So, and it is said that in India, this is crucial. Energy efficiency or sustainability is crucial in coming times because 80% of India is yet to be built, and we are going to see a lot of urbanization coming in next couple of years, and a lot of these rural population is going to move to urbanized area. So essentially it is important that we make our building which are sustainable. So coming to the question, you can ask what do you mean by sustainable buildings, and how do you design it, and what is different in a sustainable building design as compared to a standalone or a standard building? So let's look at that. So we have a traditional approach towards a building design which typically follows a linear step by step process where each discipline, like such as architects, structural engineers, mechanical engineers, all of these would work specifically in isolation, in parts. So say for example, architect would work on design, MEP consultant would work on the essentially what kind of HVAC systems would come in. Electrical would work on the kind of lighting systems would come in, and all of that won't. All of these people would be working in silos, not in tandem. So they'll have some sort of discussion on regular interval, but they might not have a sort of a discussions which would bring in integrated design approach. So let's look at it. What is different in terms of when I say integrated design approach? So integrated design approach for building involves a collaborative process. So where all stakeholders like say architects, engineers, contractors, building owners, users work together to form right from the early stage of the project. So this approach focuses specifically in optimizing the building performance, considering all aspects such as energy efficiency, material, system, site condition, everything in a particular manner. So it's a very different kind of approach as compared to traditional approach, and we'll see more of this in energy efficient buildings. We'll see more of this in sustainable building design. So if we look at any particular rating system also, so say IGBC, GRIHA or LEED, they all talk about the integrated design approach. It's crucial for any particular high performance building design. So I'll tell you from example that the net zero projects, so net zero energy projects which I have worked on specifically have this kind of approach where all consultants come and have set goals from day one and ensure that everyone is on same pace. So what is sustainable design? So we talked about integrated design, right? Then what is this sustainable design approach? So if you look at any particular building, there are 5 major energy consuming sectors in that particular building: lighting, cooling, equipment, fans and pumps to pump water or whatsoever, and hot water requirements. So this is total energy, which this will give us total energy which is used in a particular building. So high performance building, when we talk about, or sustainable building when we talk about, it takes in account resource efficiency and without compromising comfort and health and well-being of the occupant. So this is the sustainable design approach. And way to design up. So what is the way to sustainable design approach? It's simple. It's divided into 4 ways. So first we start reducing the energy demand through various measures like through building geometry, natural ventilation and daylighting. So all of these we start incorporating passive design measures, which is part of step 1. Step 2, we reduce energy demand by incorporating energy saving measures like building envelope designing, lighting design, thermal storage system, all of that. So that is how we reduce energy. Step 3 is high efficient cooling and heating system. So 60% of the overall energy which is used in a building goes into heating and cooling. It actually is a very crucial aspect if we look at the overall energy performance in a particular building. So we design that efficiently. And the step 4 is incorporating renewable energy systems like solar PV or wind turbines or biomass to curtail all of these, or say I would say to balance all of the energy which is used in a particular building. So a net zero building, when we talk about, is a concept where whatever energy which you are consuming in a particular building, made, as I said, made before lighting, equipment, or HVAC system, whatever you are consuming across the year, you are generating the same amount of energy through a renewable energy system on site. So when we talk about prioritizing the right aspects in the building, so if we look at this, let's look at two of these graphs. So the graph in left actually shows about the x-axis, shows about time in year, and the y-axis shows about the replacement. And these are sort of parameters which we consider during the design phases. Say, for example, foundation, structure, facade, mechanical equipment, furniture, IT, all of these. So these are crucial aspects, right? But if we look at these, so number of years these things would survive and how often you will require to change it. So we look at foundation, structure, and facade are the three elements which are going to last more than 70-75 years. So even if you change all of the interiors, that's a possible. You'll have to change, say, in even if you look at your house, right? You might have to change your interiors every 5 years or so, because your requirements would change over the period of time. However, facade, structure, and foundation are going to remain for the longer period of time, so we have to ensure that these are going to be sustainable. So if we look at high performance design parameters, it is divided into 7 steps or 7 aspects. First is sustainable site, which talks about accessible amenities, where we talk about pedestrian comfort and green cover, how accessible a site is as compared to a nearest metro station or a railway station or a bus stop, to ensure that there is a friendly and easy commute to the site. The second aspect talks about materiality and materials. So where we talk about use of natural materials, how natural materials we are incorporating in a particular building. That can be terracotta, or that can be various other kind of green building materials or a green concrete of a kind. Then we have water management. So water management would talk about use of as much as less water. We talk about water efficient campus or net zero or a water positive campus, where whatever water you are using or consuming across the year, you are replenishing the same through groundwater recharge or rainwater harvesting system. So that is what we have in water management. Then we talk about health and well-being. So here health and well-being are crucial aspect in any particular building design, right? So we want our occupants healthy, and say, for example, let's look into any particular building. If the space is more, you will feel that if any particular naturally ventilated space or a space which would have a good amount of daylighting, then those spaces are tend to be more invitable as compared to dingy and smelly places, right? And occupants would also like to be in those kind of spaces for a longer period of time. So health and well-being aspect prioritize fresh air, glare-free daylighting, say pollution or dust control, and acoustic controls. The fifth aspect of it is energy. So energy talks about energy efficient building design, where we are reducing the amount of energy which we are using across the year. Waste talks about circular economy, where we talk about waste management, organic waste management on site, segregating all kind of waste, and then have some sort of central utility where all of this waste is segregated in terms of dry, wet, plastic, paper, and then that is given out to third party vendors. So that is a proper waste management. Then we talk about thermal comfort. So all buildings are designed for thermal comfort, correct? So we ensure that these factors in terms of temperatures and humidity are maintained across the year to meet the thermal comfort requirement. So then these parameters, what design parameters one should account for at which of the design stages. So if we look at any particular building design, there are particularly 3 design stages. One is concept, second is schematic, and third is detailed design stage. And all of these parameters would come in at a different design stages. So let's look at early stage or a concept design stage. In this, we'll look into requirements such as what are the client vision and budget, what is the density. We'll look into the site context, what is the hydrogeological. So we'll do sort of a hydrogeological survey of the project or the site, understand connectivity to public utilities. We'll start looking into the climate and the local vernacular kind of architecture through which the design would be governed. At schematic design stage, we'll we look deeper into the architectural design as the design, establishes further in detail. We look into facade design, we look into passive design, integration, what kind of passive measures which we can integrate in design. We look into details of MEP systems which can come in, sort of landscaping, what kind of landscaping which we'll want to do. All of that comes into schematic design. Then aspects related to detailed design. So here the design will more be detailed in terms of what kind of materials will be going into the facade, the kind of shading devices, interior detail, interior layouts, structural system, all of that would come into detailed design stage. So there will be different kind of studies one needs to do in each of these design stage, and then there are different kind of tools which one will require in terms of simulation at each of these design stage. I'll talk about it in upcoming slides. So if we look at early design, so at concept stage, we'll finalize a lot of things, right? So we'll finalize orientation of the building for a typical campus. If we look at it, how we are going to orient a building, north, south, east, west, what is the spacing and the height of the building. We'll have some sort of a clarity from the client, what is the kind of FSI which you are looking forward to, what are the design requirements. So based on that, we'll start finalizing the orientation, spacing and the height of each of this building. We'll start looking into various aspects of climate and the local vernacular architecture. What will be the build and no build zone? So how the kind of landscaping is going to evolve. We'll start looking into the pathways connecting all of these buildings. Shape and the form of the building will be designed at concept stage. So all of this would come in. So it is important that there are so we have a combination of architects, sustainability consultant, MEP consultant, and landscape consultant. All of these people have to come in from the concept design stage itself to finalize all of these aspects, rather than having only architects to do these and then later on that is translated to other consultant. It would be ideal if all of these consultants come right from the early design stage or say concept stage to work on a scheme which is more sustainable. Why? Okay, so the next slide is going to answer your question to the why. So this is on the graph you can see is McLamy curve, which shows the cost as this shows the cost on the y-axis, and and on the x-axis you can see are the specific design stages. So here what you can see is that the curve specifically shows that as design progresses, costs to make a significant change or impact would be much higher, whereas impact can be made at a much lower cost at early design stages. So this means that for a high performance building design you'll have to make lot of iterations from the get go. So for example, for efficient envelope you'll have to define the kind of insulation you'll be using, the kind of facade which you are going to work with, window to wall area ratio, or the kind of if you're using bricks or AAC blocks. Rather than all of those things coming in at a later design stage, it's essential that we decide all of those right from the concept design stage. That's going to impact a lot of things. So say for example, your facade iterations or facade changes are going to have an impact on your MEP systems, HVAC systems, the amount of tonnage of cooling which will be required for a particular building. It would be different if it has material like AAC block. It would be different if it has material like bricks. It would be different if your WWR, window to wall area ratio, is 30%. It will be different if you have window to wall area of 60%. So all of these are going to play a major role when we do a system design and later on other set of designing as well. So it's important that all of the consultant come into the design phase right from the get-go. So what we have heard is there's a myth around green buildings that green buildings are super expensive. That first thing when even I pitch sustainable design or net zero building design to a client, the first question which I get asked is, how expensive is it? We have heard that green buildings are like 15 to 20% more expensive as compared to regular buildings. Again, this is a myth. So green building designing is a collaborative process, and if done in a right manner, using the integrative design process, we can definitely save a lot on operational costs through energy savings without affecting any capital expenditure. on a particular project. I want to specify this again, that there is a very low or a minimal change in capex of a green building as compared to a typical building, if the designing is done in a right manner. So how do you design in a right manner? So first we said that integrative design approach, yes, you have to ensure that all consultants are on a same page when we are designing a sustainable building. We clear out that these are sort of requirements, these are the goals which we are going to look into in terms of energy waste, water and others. But there's a performance based design approach when we talk about green building. So we look into we look into aspects like climate, site. We ensure that the building is in tandem with the site. We ensure that there are sort of local and vernacular architecture principles which are embedded, which would help in passive design, selection of passive design strategies on the site. We ensure that there are proper facade materials which are selected. We ensure that the building is oriented in a right direction. So for what I mean by building orientation in the right direction is that if say for a climate like Delhi, if you have a lot of windows specifically in east and west, you won't be able to shade it across the year, and you will receive ample amount of sunlight on those both facades, and you won't be able to shade it. So you have to ensure that your building is oriented in a right manner, and it also has an impact on energy savings in a particular building. So say for example, let's look at an office building in Delhi. If it's oriented in north south, longer axis, you will save somewhere around 1 to 2% annual energy as compared to a building which is oriented east and west with say 60% of window to wall area ratio. This would also depend on a lot of other situations and conditions, but this is a generalized example on that front. So all of these are important. So there is a typical methodology for energy efficient building design. So here there are different kind of studies which are required at different stages. So for example, at concept stage, we do climate studies to understand passive design strategies one can propose. The passive strategies like massing studies to determine orientation and geometry. Here you can see these are studies which are done to understand orientation and geometry. Then we have natural ventilation studies using CFD. Then we can do for say CFD for naturally ventilated spaces or atriums or outdoor spaces like podiums. Then we have solar PV potential studies. Then we have UTCI studies, which specifically talks about outdoor thermal comfort and pedestrian comfort. The input are shared with client based on these. At schematic design, we have studies like shading studies, daylighting studies. These are daylighting studies. Then energy modeling studies for a selection of energy efficient envelope system, waste calculation, water calculation. All of these are done at schematic design stage. Then at the detailed design stage, we do sort of energy modeling for system selection. So for example, if I want to select a system like evaporative cooling as compared to your traditional split unit, then I'll be doing a study, sort of detailed energy analysis study during a detailed design stage to understand what kind of system is going to be more efficient and what is the kind of energy savings which I'll be getting from that kind of a system. Then we do sort of life cycle carbon analysis also at this particular stage. Then let's look at the kind of simulation softwares which one needs to use in these kind of studies. So for example, at the early design stage or the concept stage, there are these kind of tools which I have used to do the studies earlier. So you saw in the earlier slide, right? We have done all of these kind of studies. So we use tools like Rhino and Grasshopper. So Rhino and Grasshopper as a family has a tool set called as Ladybug tool set, which has various other tools like Ladybug, Honeybee, Butterfly, Dragonfly. All of these are used. So that is sort of a tool set which is done, which is by Ladybug tool. It is an open source and very effective to do certain set of simulation. I'll show what kind of simulations can be done in these. Then we have again free to use and based on a 3D system. So modeling is pretty simple and easy like SketchUp. So definitely I'll suggest using Ladybug toolset. And Lot of resources are available online for free to use these tools. Then we have Autodesk Flow Design. This is by Autodesk. This is basically a simulation tool for airflow simulation. So as I say, for natural ventilation potential, we require certain set of studies, and Autodesk Flow Design used for the same. Then we have something called as Yumi and Urban Daylight. So this again is a plugin to Rhino and Grasshopper. This is used for aspects like early stage energy simulations, walkability, schematic design, or embodied carbon calculation on a larger scale. At a say I would say even at a city scale, if you can use these kind of tools. Then we have Envimet, which is a very detailed simulation software. It uses this is basic. This is used for basic wind simulation for large scale for a point in time airflow. Again, this can be used for one point in time across the year. So a very interesting software for urban design. So for example, Ladybug family. So Ladybug family, one tool which is Ladybug. This is used for climate analysis, radiation analysis, outdoor thermal comfort, and others. So here in the upcoming slides, I'll explain what will come under all of these and what kind of inferences one can take from these kind of studies. So here we have this. Then Honeybee we can use for outdoor thermal comfort, sensitivity mapping for vegetation. So how shading would impact on a particular design. We can do daylighting also in Honeybee. Then we have Ladybug tool called as Butterfly. So Butterfly is essentially for wind analysis, for natural to study the natural ventilation potential. So Autodesk Flow, again a very interesting tool and a software which is used for wind analysis. Here you can see a typical wind analysis done for a particular campus for in Noida. Here then we have Yumi and UD, right? We discussed earlier. So this is for iterative quick studies for radiation and daylighting, again done on a very large scale. Envimet, so these are sort of visuals from Envimet, and this is the kind of data it's going to give us for studies like wind, air, temperature, humidity, comfort, all of that. So then Ladybug Honeybee. So the other plugin which we discussed earlier, right? This is for all detailed design stage. Earlier, where for concept design, these are detailed designs stage tools. So Honeybee we use for daylighting. There are other tools also available like Climate Studio, where you can do the daylighting analysis easier. Then for energy simulation, very important aspect, there are a lot of tools which one can use. So if we look at it, there are 4 tools which use different simulation engine. So Energy Plus is a simulation engine, and we have three design interfaces, 3 interfaces of softwares which can do simulation using the Energy Plus, which is widely used in the industry. That is DesignBuilder, Energy Plus. Energy Plus has its own interface. IronBug, which is again a bug by Ladybug family, and then Open Studio. So DesignBuilder is paid version. Energy Plus is free. IronBug again is free because it's part of Ladybug family. And then Open Studio again is based on SketchUp as a node. So again, it is free. If we look at other set of tools, so we have ISVE, which is industry recognized in terms of energy simulation. It is used in lot of countries, so in geographies essentially. So IES is very well taken up in US, in Middle East region, and others. EQuest again, EQuest is lot of it is used in USA and in India as well because it's free. ISV is paid. EDSLTAS, which is used in European countries, both of those are paid. EQuest is free, but however, it is a quick simulation software. It takes much lesser time as compared to all the simulation tools which I explained in terms of energy simulation, because it is based on static calculation. All of these other simulation softwares use dynamic methodology to calculate the energy use. However, EQuest uses a static steady flow and static calculations to come up with the results. However, if you look at any particular naturally ventilated buildings, EQuest won't be used in naturally ventilated building. It can be only used for air conditioned buildings. However, IES, EDSLTAS, DesignBuilder, Open Studio can work very well with naturally ventilated buildings. You'll be able to get the comfort results out in terms of comfort results as well as energy outputs out in those kind of softwares. So we saw what are the kind of tools which we can use in early stage or detailed design stage, but how do these tools help? So it's important to understand how to use these set of tools. These tools would help into finalizing these aspects like orientation, shape and form of the building, spacing and the height between the building, floor plate and the depth. So through various kind of simulations like daylighting, energy, shading, etc. And this would influence design in terms of facade design, glazing design. So deciding what is the kind of WWR, external shading, where the shading should be provided, east or west, north or south, or what kind of shading device. Is it horizontal is going to be good enough to shade south, or do we require vertical shading design? What angle, what depth, all of that. Then interior layouts. So interior layouts to ensure that there is enough daylighting in a particular space. Rather than having dingy spaces, we would want to have inviting spaces and glare free daylight spaces. So essentially this is all going to help, these tools which are going to help in designing these four aspects, and this is going to help finalize these aspects like facade, glazing, external shading, and interior layouts of a particular building. And this would as I said, this would have an impact on daylight ingress, which would lead to lighting loads and visual comfort. This would have an impact on ventilation and heat ingress. So your envelope would have an impact on ventilation and heat ingress and thermal comfort, which would rather guide HVAC systems and cooling load. So these all tools are required, and this is going to inform the designing process. So, and this is the conversation that forms the basis of a design development. And these sort of results has to guide the designing process, where all of these consultants like architects, contractors, owners, consultants, engineers will come together and have these conversations to ensure that these are done right at the correct stage. So now let's look at a case study to understand this in a more depth. So let's look at a case study for a net zero campus in Delhi. I was working on this project for a very long time, and I have done certain set of studies, and based on that we have inferences how that would and how that will be impacting the design process. So we'll come through that. So the first step for any particular sustainable building design is goal setting. So what do you mean by goal setting? So we understand we decide what are the key themes for that particular project. So for this particular project, it was carbon, energy, water, circular economy, health and well-being, biodiversity, equity, and resilience, because these were in tandem with company's requirement as well. So this was a project for a MNC building, which was a multinational corporation which had a net zero goal for 2030. So company wanted all its assets which are in India to be net zero by 2030. So essentially there was the goal setting was done across these lines, which were also part of the ESG framework of that particular company. So then what we started was we started listing KPI, so key performance indicators, based on which we'll be able to design our building. So after goals, we have KPIs which are established for all of these 8 parameters which I said: energy, carbon, water, circular economy. So for let's look at how we define a KPI. So for example, company have as I said, company have a carbon neutral campus by 2030 is the goal. So the first thing was they need to do is decarbonize its fleet. So they have a pickup and drop services which is provided to its employee, and we said, we need to decarbonize your overall fleet or the shuttle service we are providing for that particular project, and from the get-go, from the starting of the project. And for that we are suggesting to provide 20 to 25% of parking space for electric vehicles, or have a charging facility developed for those EVs. So for example, energy. So energy, they wanted to be net zero by 2030. So we suggested, okay, fair enough. We understood what is the kind of building energy usage. We got the data of how their other buildings are operating, and based on that and the solar PV potential on that particular site, we suggested all new buildings to have energy performance index. So the EPI again is defined as total energy used divided by total area. So we said that your EPI should be around 60 kilowatt hour per meter square per year in all new buildings. So that should be, so what kind of strategies would come in? So strategies like efficient envelope, HVAC system, be 4-star and above rated, equipments. So these are a requirement, right? So, and we suggested efficient building envelope systems and energy systems like radiant cooling and others. So that is how the KPIs were designed. So we have the overall goals, then we start looking at KPIs. These are the indicators through which we'll be able to measure how we are performing, and then we have strategies for it. So say for example, we have water. So water, we are suggesting goal of being a water positive campus by 2030. KPI would be to reduce the overall water consumption, indoor water consumption by 50%. And the strategy to reduce the same would be through efficient water flow fixtures, to have efficient irrigation systems and others. So similarly, we develop these goals, KPIs, and strategies for all of these aspects, for health and well-being, for biodiversity, equity, and climate resilience. So these are the kind of KPIs and goals which were established. So now, after doing KPIs and goals, the next step for us was to understand the climate analysis. So we did a sort of a climate analysis study for this particular campus. So as per both NBC and ECBC, which use a climate classification system to categorize different part of the country based on the climate condition, Delhi falls under temperate zone, which means the summers are extremely high, where temperatures goes from 40 to 41 degrees, and winters are cold, where temperature falls below 10 degrees. So these are kind of climatic charts which we developed, climate and humidity, dry bulb temperature, your air temperature and humidity, to understand what are the levels in all of these seasons, like winter, monsoon, summer months. And then based on that, we did a study, wind studies as well. So these are kind of solar irradiation studies which are done for winter, summer, and monsoon months. So this essentially talks about the solar irradiation and what horizon is it falling on. So for example, winter, the sun comes from south more or less across the year. Summer, you have the sun coming in, the high radiation on the upper top hemisphere. So it's very difficult to shade the summer sun. And monsoon, again, we have a from on the more from the southern and the east and west side. Similarly, we did a wind analysis here. What we found was the predominant wind direction is northeast and southwest. Northeast essentially during winter and summer months, and monsoon it is again west to east. So based on this, we suggested certain set of passive design strategies like shading, natural ventilation, and window positioning based on these wind analysis. So again, as I said, that once we have these kind of studies which are readily available, we'll be able to make more informed design decision based on it. And these are the design decisions which come from these, like as I said, shading or kind of opening, the placement of opening, all of that. What kind of WWR which would be recommending. So then we did sort of a resilience study. So resilience study, for this we did sort of a short literature review, and these are sort of potential climate hazards which one can see in Noida. One being urban urban heat. So again, we are seeing this, that heat waves are going, being more frequent in coming years. Water scarcity. We saw that in last year's newspaper that water scarcity is a big issue in major cities now. May it be Delhi, may it be Bangalore, Chennai, and lot of other cities are going to face in future. Then the third climate hazard was air pollution, which is the most crucial and important one. Climate hazard in Delhi is very crucial, because say 1 in 6 people actually in Delhi have issues because of air pollution, so breathing issues specifically. And if it's said that staying in Delhi is like smoking 6 cigarettes a day. So it's all of this is important when we are designing a building, because there are a lot of recommendations, a lot of changes which we can do in terms of design based on these studies. So for example, urban heat, we can have high SRI paints across the campus. On roofs, you can have high tree cover on the road. All of that can be done to improve the urban heat. For water scarcity, you can have features like rainwater harvesting, water conservation fixtures to reduce the water usage, and then have rainwater harvesting and aquifer recharge and wastewater recycling kind of a system to meet the water demand of that particular campus, ensuring that you don't have to get the water from outside, specifically during the summer seasons. Air to combat air pollution, we suggested certain set of filtration systems like MERV 13 or high quality air filtration system in the HVAC systems which were installed, or air conditioning systems essentially. We also suggested sort of having a tree barrier across the campus boundary to ensure that to reduce the overall air pollution, because that would reduce your not directly the CO2 but PM 2.5 PM 10 levels are reduced because of the tree barriers and buffers. So these are kind of informed decision making which would come from these kind of studies. This is again an interesting chart which talks about UTCI. So this is Universal Thermal Climate Index. This essentially is for outdoor thermal comfort and to ensure that we have pedestrian thermal comfort. A lot of times what happens is that we design for a pedestrian campus, but however in hot climates like Delhi, people are not able to use it specifically during the afternoon time. So if you ask someone to walk say 500 meters from an office building to a canteen in hot summer at 3 in the afternoon in month of June, people are not going to go and walk if unless and until you don't provide a proper infrastructure for them to walk. So you'll have to have proper shaded walkways under which they'll be able to walk and go, because that is something which you also would have faced, right? So if you're sitting right under the direct sunlight, you'll face lot and you'll feel like temperatures are somewhere around 40-45. But if you are in a shaded place, you'll feel somewhere around 35 or 38, which is manageable, which you'll be able to feel comfortable across. So so pedestrian comfort is very crucial when we are designing a pedestrian friendly campus and where we want people to walk in. So here the objective of this study is to explore the most effective passive strategies, what kind of shading elements would work and what kind of shading orientation would work for pedestrian comfort. So on the right, you can see the temperatures here. So these are temperatures across the year. So this is for May, typical summer month, right? May 9 a.m., 2 p.m. and 5 p.m. So here we can see that there is a strong heat stress which is observed. So temperatures are from 40 to 42 degrees. So we suggested features here like shaded walkways for pedestrian comfort. So shading that can be done through your pergolas or through your trees. Then and to improve the vegetation in particular campus, and kind of materials which has to be selected for the shading of these walkways. That is also crucial. For example, I was working on a campus which was in Hyderabad, a beautiful campus, specifically a school that was for a school building. What happened was specifically we had a site visit during winter months. Beautiful walkways they had. These were they had pergolas which were made out of aluminium, and then they had creepers running across those, and very beautiful, specifically in monsoon and winter's time. But we visited the same campus in summer. The whole the whole greenery on the top of those pergolas, where you had those creepers, all of those were charred. It was like burnt charcoal, because the temperatures in Hyderabad goes to 40-45 degrees, and the temperatures of your aluminium section or MS section which was used, those were also higher. So that would go somewhere in 60-65. So that would char your creepers or your plants. So selection of your materials, especially for outdoor thermal comfort, are also very crucial. You would want walkways which are not concrete, because concrete would essentially reflect lot of heat into the space. So we would like to, so all of these studies would help you in selection of right kind of material for your external thermal comfort. Coming to the next aspect, which is solar irradiation studies. So these are kind of studies which are done to understand the amount of shading, the amount of sunlight on each particular facade. So for example, if we look at it here, you'll see a lot of red, right? So red would essentially mean that your irradiation levels are somewhere around 1,000-1,500, and blue would mean that your irradiation levels are lower. Orange means moderate. So what you would see in south and west, essentially, your irradiation levels are going beyond somewhere around 1,000, which is high. So that would mean that you will require a lot of shading in south and west direction as compared to north and east direction. So we have seen that as an architect student as well, right? So that in north you don't generally require shading, south you will require shading, east and west definitely will require shading for some times across the year, uh, and it is very difficult to shade both east and west. So these are kind of recommendations which we'll get from solar irradiation study. Again, the tool used here was Ladybug toolset. Then we had something called as sonar analysis. So this essentially helps in calculating the solar PV potential. So for this particular campus, we said that for let's look at this campus. So we can have solar panels both on the rooftop, not all of the rooftop, but say 70 to 80% of the rooftop. And then we can have solar PVs also installed on walkways as a strategy, or on the parking. So these tools essentially help us to understand what will be the solar potential, how much solar energy can we generate if we have solar panels on the rooftop and on the parking. So these are the kind of numbers in terms of annual energy generation which one can get through sonar analysis. Again, this was done on Honeybee, which is again a plug into Rhino. CFD, very interesting. So this is computational fluid dynamics, a very complex simulation tool, as well as very interesting study to be done. So we as an architect believe that, drawing arrows in a direction is how the wind will flow. That's not the case always. So natural ventilation in the building design is very crucial. And then it depends on a lot of aspects. So it depends on the wind direction, wind velocity, and size of opening. So we saw wind direction and wind velocity in the climate study on earlier, right? But again, sizing of the opening and the direction of openings are crucial when we design for natural ventilation. So for that, we have to use CFD as a study. It is simplified vector analysis to predict comfort and natural ventilation potential in a particular space. This essentially, the objective is to assess the wind flow of the proposed build form, and provide windows and openings in the windward direction essentially, and to design for the both occupant comfort in naturally ventilated spaces as well as pedestrian comfort, and provide windows and openings in direction of higher wind speed in monsoon, specifically to streamline the wind movement inside the building and enhance natural ventilation. So based on this, we have a lot of recommendations based on these studies. So for example, let's look at this. So here, the red portion would mean that you have a higher wind speeds, okay? And the moment you have the most blue ones, this means that these are the leeward direction. This is the windward direction, and the dark blue is the leeward direction. So essentially, what would you want is that in one of the directions, you would want higher wind speed. So for example, we don't want winter winds to be coming in climate like Delhi, but we will definitely want monsoon winds and summer winds, monsoon winds to come in for the natural ventilation potential. So here what we do is we do a simulation for one particular direction. So here you can see that we did a simulation for four direction: northwest, west, southeast, and east. Each one for each direction. And what we saw is that, so for this particular building, we wanted to ensure that we have one particular windward direction and one leeward. So we'll be having proper natural ventilation inside a particular space. So that's how it happens. So daylighting study. So daylighting, again, the objective is to determine the maximum hours of daylighting available on a regular basis in a regularly occupied building. These will depend on a lot of aspects. This will depend on the orientation of building, what is the window to wall area ratio, what is the size of opening, what is the distance between each opening. So again, a very interesting and important kind of study. So here, so for example, here if we look at the study, so window to wall area, so if we look at a WWR of 30, 40, and 50%, the daylight autonomy, the amount of daylight which is coming into the space is different for all of these. So we can see with WWR 50%, the amount of glare. So this specifically talks about the percentage of time across the year. So you will see that one will observe maximum amount of daylight specifically on periphery, which can cause glare issues. However, if we look at WWR of 30%, the uniformity of the daylight is much better in that particular. So these kind of study can inform on lot of things like shading which will be required, what kind of shading device one will require in terms of, say, for light shelves, or you can use vertical panels, or you can have horizontal pergolas, or a fixed shading device, what kind of VLT, or what kind of visual transmittance will be required in glazing to have a proper kind of uniform daylight space. All of this would come through daylighting study. So here the tool which was used for daylighting study was Honeybee. Again, forgot to tell you about CFD. For CFD, I had earlier study which was CFD. I had used uh, one which is called Butterfly, which is a plugin to Rhino. Again, looking into detailed studies. So these are the daylighting and energy studies are generally done during the detailed design stage. So this essentially talks about the sensitivity analysis, which was done at the detailed design stage. So here, this helps in determining major variable influencing building thermal performance using both observational research and energy simulation models. So the objective is to understand heat gains through different wall assemblies. So basically, if you look at these kind of this chart below, these are kind of U values uh, of a particular building. So for example, U value of a typical brick wall will be 2.2, and the one with the insulation is 0.2. A typical AAC block will give you a U value of 0.8, 0.7, which is this. And this graph talks about effective cooling area per tonnage. So how much square feet per ton will be required in terms of cooling, and this is percentage improvement. So this tells you that the lower the U value is, the more insulated the space is, you will achieve more improvement in terms of cooling square feet per ton number. So more effective cooling area. That would mean your air conditioning requirement would go lower. However, your cost because of insulation is going to be higher. Similarly, this is on the chart on the right shows about the EUI of building. EUI is your annual energy usage index. So these numbers talks about the EUI. So that is your annual energy consumption per year. And on the bottom you have the U values, which goes from 2.2, again typical brick, to insulation of zero point 0.2. So what you can see is that the higher the amount of insulation you have, the amount of overall EUI of a particular building starts decreasing in this case. So the amount of savings which is it's going to increase over this case. But however, there is some sort of a point of diminishing return, where you'll have to select a material which won't have so much impact on energy, which will have a significant impact in terms of energy savings, but however not so significant impact in terms of cost. So these all numbers or data which one can get from energy studies through simulation softwares like EQuest, DesignBuilder, ISVE, and others. So if we look at how this would fare in terms of recommendations. So if we look at recommendation based on these studies, we see in two aspects. One is master planning level, at campus level design, and the other is at building level design. So at master planning, these are sort of recommendations which these studies would provide. So say for example, this gave us inference of using roofing material which would have higher solar reflective index. So that would reduce your overall requirement for that would reduce your urban heat island effect. Then the second was all high activity or activity zones, transition spaces and roads to have a fixed shading device or trees. Fixed shading device, again looking at the materials, it was a combination of bamboo and the creepers, or it can be trees, or it can be solar PVs. Then we suggested the other recommendation or the inference from this was having high amount of parking spaces which will have electric charging facilities, having deciduous and evergreen trees in walkways and parking areas, because we didn't want those to shed leaves during specifically autumn, and have impact on the thermal comfort of the occupants. Then it was to provide vernacular access to central waste collection area, so having impact on the waste and the water management in the campus. So these are sort of recommendations which one can get, or inferences which one can get from at the master planning level through these studies. Then we had recommendations in, or say building level recommendations or inferences from these studies, like we went to ensure that we restrict the window to wall area ratio of the project to 40%. We didn't want to go higher than that. Then providing shading, so we wanted to ensure that we have overhangs specifically in southern facade to reduce the amount of heat ingress. We have to have certain shading devices like fins specifically in east direction and west direction to reduce the uh, amount of heat gains. We suggested having particular set of VLT. So we suggested visual light transmittance of glass of more than somewhere around 50. We suggested U values based on these studies. So U values are your thermal conductance of a property, thermal conductive property of envelope materials. We suggested uh, typical sort of a set assembly with for this would be different for each orientation. So for south, east and west, we suggested the concrete blocks with insulation of 50 for north, we suggested AAC block. So these are kind of recommendations which one can get from these kind of studies, very crucial and important. So and with this I'd like to end the presentation and I'm open for questions.
Thank you, Mansi. I think this was a really insightful presentation. And, like, with the constant growth in the need for sustainable and energy efficient built spaces, it has become really crucial for design decisions to be aligned with what the environment needs as well. So
Absolutely.
your detailed inputs into the tools that we can use into making your buildings green and energy efficient. I think all the viewers, they must have really been inspired by this. And with such informative workshops, let us hope that the Indian design approach shifts from what it is right now. We are actually seeing a shift in the design approach, but let us hope it goes beyond this as well.
Absolutely. Looking forward to the same.
Yeah. I hope you had a good time with us here today.
Absolutely. I did. Simran, thank you. It was wonderful
Yes.
session.
It was really, I think, insightful. Every detail that you mentioned, from site level, master planning level, inputs that we need, to basic building approach, what we need to do. It was all wonderful to even listen to it. I mean, I think 1 hour was not enough for your presentation actually to be over. You had so much to say, but yeah, I look forward to more such collaborations with you.
Absolutely, Simran. Looking forward to the same as well. Thank you.
Yes.
Thank you for
Thank
giving me this opportunity. I hope the audience loved it too.
Okay, thank you, Mansi.